Welcome to FEA Insight and FEA Academy YouTube channel. Master Finite Element Analysis with our comprehensive series of videos tailored to both beginners and experienced engineers. Explore fundamental concepts, advanced techniques, and real-world applications through case studies and practical tips. Stay updated with the latest developments in FEA, empowering you to excel in your engineering career. Hello everyone, welcome to this new episode of FEA Insight. Today we're going to talk about working with finite element analysis. Here is the agenda. First, I want to answer the question how FEA can help you, and I'm going to present you the FEA process, also the capabilities of the FEA software. Then I'm going to answer three fundamental questions. How accurate is FEA? Why doing FEA? And what is needed to perform a finite element analysis? So let's start this part by how FEA can help you. FEA is helpful for all specialists involved in product development. First, the stress and structural engineers, the dynamic engineers, the loads engineers, and the designers. FEA can assist all the specialists in developing products. It helps them to make decisions during all phases of the product development and to answer the following questions. First, will it break? Will it deform too much? Will it hold together? Where are the weakest points in the structure? And can it be lighter? And can it be stronger? And finally, will it work the way it was designed to? There are 7 situations where FEA can help you. FEA is used to solve complex problems of engineering and is useful for problems with complicated geometries, loading, and material properties in which analytical solutions are not applicable. You can use FEA in multiphysics problems to provide solutions that would otherwise be impossible to solve with the classical methods. With FEA, you can predict the response of mechanical structures to environmental factors such as forces, pressure, temperature, vibration, etc. For engineers, FEA is an important part of the product design phase in an iterative development process because it saves engineers time and reduces the effort and cost associated with building physical prototypes. During the product development process, simulation software that have FEA functionality are used to define the deformations and the stresses that the components will undergo when subjected with environmental factors. By component here, I'm talking about the component which compose the system that we want to build and analyze. The FEA packages are extremely powerful when used intelligently and help the engineers to define the critical dimensions of a component by considering the factors of safety, the weight, and many other parameters. FEA can be as simple as addressing a single part for which you wish to capture the behavior, but also it can be more complex. Indeed, complex analysis may involve multiple parts for which you wish to predict the interactions. So it means that you can build a simulation where multiple parts are connected together and interact together. So here are the common cases where finite element analysis is used by engineers to solve complex problems. First, we have the typical structural strength design, okay? The structural interaction with fluid flows, acoustic problems, thermal analysis, vibration analysis, crash simulation, fluid flow, the computational fluid dynamic, for example, aerodynamic, the buckling problems, which are the stability problems, the dynamic analysis, and the electromagnetic evaluations, and finally, metal forming. FEA is useful at every stage of product design. Before to define the product, FEA helps the engineer create a feasible design, okay, by analyzing many situations. After the product is designed, FEA permits the validation of the defined design. But also after the product is released, indeed, FEA can be used to investigate product failures. So FEA permits the engineer to make great products by delivering better design quickly. When an engineer is working with FEA, he has to follow a basic process. So here I'm going to present you the FEA process from the engineer perspective. Okay? So it starts with the discretization. The engineer has to select the element type, okay, and is going to represent the physical components from the CAD. And by discretization here, we are talking about the meshing of the system. Then he has to apply geometrical and material properties to the discretization, to the elements. Then he has to apply the boundary condition. Why? Because it's going to dictate the behavior of the system at its boundary, and it will make it solvable by the computer. Then the analyst has to apply the environmental factors, the force, the pressure, the thermal effect, the vibration effects that the system will undergo in the reality. And finally, the problem will be solved in order to satisfy the equilibrium equations, and this solving is done by the computer. Now let's see the FEA process from the solver perspective. Okay? First, the solver has to evaluate the stiffness matrices of the individual elements which compose the discretization, the meshing. Then the computer, the solver I should say, is going to assemble the global stiffness matrix of the analyzed system. Then the boundary conditions are going to be applied on the global stiffness system, on the matrix problem. And the solver is going to compute the equilibrium equations to obtain displacement. Then, from the displacements vector obtained by the computer, the forces, the stresses, velocity, acceleration, strain, energy, etc. are going to be calculated by the solver. The commercial FEA software can solve a variety of single and multi-physics problems, including structural problems and issues of heat transfer, fluid dynamic, acoustic, magnetism, electrical fields, etc. Okay? The structural engineers use FEA to ensure that the structure has the necessary strength, stiffness, or life to prevent failure due to an excess of stress, resonance, buckling, or detrimental deformation that may compromise the structural integrity. Here in this slide, I show you the various capabilities with the associated outcome when engineers are using FEA. So let's start with the FEA capabilities. You have different scenarios: the linear static analysis, the linear buckling, the non-linear static and buckling, the normal mode, the linear dynamic, the non-linear dynamic. Here are the different solutions that you can submit on a problem, on a simulation. And you can see for those conditions, those solutions, you have access to different capabilities. And you see, it's a wide range of capabilities. So it's like finite element analysis is unlimited. Okay? Finally, you have the FEA outcomes. It can be the displacement, force, the reaction at support, the stress tensor, the principal stresses or the von Mises stresses, the strain energy, the buckling factor associated with, and the associated mode shape in this case. This is for static and buckling. And for dynamic, you have also access to the natural frequency, the mode shapes, which are the deflections, similar to the deflections in dynamic, the modal mass fraction, and the response to loading. So it's again a wide range of outcomes. Let's talk about how accurate is FEA. Okay, a structural engineer performs FEA to predict the approximate response of a structure under a given excitation. So a legitimate concern is the accuracy of the prediction. First, you have to keep in mind that the accuracy of the prediction will depend on the differences between the real structure and the model. Okay? Obviously, a perfect match between the reality and the model is impossible because many assumptions are made when the structural model is built. A first assumption is made on the CAD when it is discretized by creating meshing of the different parts that compose the structure. Also, assumptions are made for the modeling of the joints. The joints are what is a joint? It is how we attach the different components of the structure. But also, we have to select a material model in order to represent the material of the structure. The raw loading also are discretized to make them understandable by the finite element model. So this assumption on the real loading will play a major role in the accuracy. Also, we're going to do assumptions about the boundary conditions between the boundary conditions of the reality versus the boundary conditions of the model. Also, the analyst selects the behavior that the FEA will capture. Each of these assumptions will produce a deviation between the real structure and the finite element model. However, there is really no way to define the real errors in the analysis. Okay? You can attempt to quantify the assumptions of the FEA to obtain a relative error. For example, analyzing bounding range of material properties will introduce the error in the material response. For steel structure, this error is very small since there is less than 1% variation in the modulus of elasticity of steel. However, when analyzing soil, for example, the error in material response could easily be 20%. The largest error in most FEAs is the result of bad boundary conditions. Incorrectly supporting your model can result in large errors that are transparent to the user. FEA can yield spectacularly accurate results when compared with physical test results. However, in a complex FEA, it is still not possible to obtain an error of less than 1% in the whole model. Okay? Generally, a target of plus minus 10% global error permits to obtain very good predictions. But this target does not prevent the occurrence of errors of less than 5% in some local regions of the FEA. So to conclude on accuracy, keep in mind that to produce a highly accurate FEA, the analyst has to pay close attention to many points and perfect them, especially if the model is composed of several assembled parts. A single component model will easily match the real life, while complex assembly will require more effort. So why do FEA? First, the capacity to model complex systems. It is a reason why we do FEA. To reduce the development time, to do analysis of different design configuration, because with FEA you will be able to evaluate different design by altering the configuration very easily. The performance and the cost of optimization. To reduce the testing for safety improvement, for faster achievement of the required quality. Okay. For improvement of data available to engineers in decision making. By that I mean by doing simulation of different scenarios, you are going to have a wide range of data available for your decision making. For the better understanding of all components of a system, allowing for a more rational design. Because with your simulation, you are going to be able to analyze, to investigate in detail the result for each component of the system. So what is needed to perform a structural finite element analysis? As an FEA analyst, you must define the following inputs to build a finite element model that represent a physical problem. The first one is the geometry. Since FEA is an iterative process between simulation and CAD definition, the initial geometries are usually obtained through CAD. Then you have the properties. The geometrical properties of structural problems includes thickness of a thin wall structure, the cross section, the inertia of cylinder structure, and so on. Okay. Then you have the material. For example, the Young modulus and the Poisson ratio are the basic material properties in linear static analysis. However, for analysis involving an inertia effect, the material density is also required. Moreover, for structure analyzed under thermal analysis, the coefficients of thermal expansions are required. Then also in nonlinear analysis, it is necessary to know the stress-strain curve of the materials involved in the analysis. Also, for the composite analysis, you will need to know the material properties of the plies, but also information about the stack-up, the orientation of the plies, the thickness of the plies, the number of plies involved in the composite structure. And you have also the loads. The loading applied to a structure may originate in different sources. First, the FEA analyst can define loading conditions directly based on design requirements, such as operating pressure and temperature, for example. With more complex loadings, the loads are sometimes defined by a dedicated group with expertise in the definition of the specific loadings applied to the structure. In this case, based on a given discretization of the structure, a discretization of all the loading conditions is provided to the FEA analyst. Finally, we have the boundary condition. To solve equilibrium equations, all rigid body displacements must be removed. So to achieve this, the FEA analyst must specify appropriate boundary condition for the finite element analysis. Practically speaking, the boundary conditions are set on the finite element model by imposing constraints to certain degrees of freedom. These boundary conditions should be representative of the reality of the structure that is being analyzed. So if you want to learn more about finite element analysis, feel free to contact me via email or on LinkedIn. See you for another episode of FEA Insight.